So in section 7.4 we are learning how to evaluate integrals using the methods of partial fractions. And before you can use partial fractions, you actually have to make sure that the degree of the denominator is higher than the degree of the numerator. And in this case it is, because the 2 is larger than the 1. So we are ready to go to use the partial fractions. The second step is to identify which of the 4 cases presented in this section this integral happens to be. Now, case 1 describes a situation in which the denominator is the product of distinct linear factors. Let's take a look at what that means, because it actually applies to this problem. In order to do that, why don't we go ahead and factor the denominator? And when we do so, we do indeed see that the denominator is made up of distinct linear factors. A linear factor simply means that the power of x is 1, and distinct means that the x is being added to a different constant. So here we have x plus 1 and x plus 2. Those are indeed distinct linear factors. Had the power been a 2 or something greater, then they would not have been linear factors. So we do indeed have a case 1 problem, so we can pick it up from there. And in order to do that, we can actually take this expression and rewrite it in terms of its partial fractions. To do that, we can write the expression as some constant a over the first linear factor plus another constant b over the second linear factor. And our challenge becomes to find the values of a and b. So what we do next is we basically want to clear out these denominators to make the equation a little more manageable. And to clear denominators, you're going to go ahead and multiply by whatever the denominator on the left side of the equation is. So we will multiply each term by x plus 1 times x plus 2. And after doing so, we're going to be able to cancel out all of the denominators. So in the first term of the equation, the x plus 2's and the x plus 1's cancel. In the second term, the x plus 1's cancel. And in the third term, the x plus 2's cancel. So let's go ahead and rewrite the equation. So we now want to solve for a first, and there are a couple of ways to do that, but perhaps the easiest way is to actually let x equal negative 1. By letting x equal negative 1, when we substitute in that value for x, we'll have 0 multiplied by b, which will cancel out the b, allowing us to solve for a. So let's go ahead and plug in negative 1 for each value of x in this equation. As mentioned, the negative 1 plus 1 is 0, and 0 multiplied by b will still be 0, so that's going to cancel away, and then we'll go ahead and solve for a. Turns out to be equal to negative 2. In a similar way, we're going to be able to solve for b. We can come up here and do that. And to solve for b, we want to eliminate the a term. And to do that, we would let x equal negative 2. We'll go ahead and plug negative 2 in for each value of x. This term is going to cancel because negative 2 plus 2 is 0. And we're left with b equaling positive 3. Now that we have the value of a and the value of b, we can actually rewrite the original integral by using those values and writing the integral as in its partial fraction form. So after using our values of a and b to rewrite the original integral in terms of its partial fractions, we obtain the following result. And this is going to be much easier to integrate than the original expression. Now, a shortcut to integrating the first and the second term is to notice that in both cases you have a denominator of x to the 1 plus some constant. And it turns out that instead of integrating using substitution, we can actually use a shortcut in those cases. So whenever the denominator is made up of x raised to the first power plus a constant, we can integrate by simply writing the natural log of the absolute value of the denominator. Now that may seem a little confusing. It is a shortcut. Please feel free to respond to the comments and I can follow up with further explanation. We also have the constant of negative 2 in the front. The second term can be integrated in a similar manner because it's x to the first power plus a constant. So that is always integratable by writing it as natural log of the absolute value of the denominator. We're going to go ahead and evaluate that from a lower limit of 1 to an upper limit of, lower limit of 0 to an upper limit of 1. So after plugging in the upper limit first and the lower limit second, we arrive at the following expression. This really turns into algebra at this point. So what we can do first is combine the terms that are inside the absolute values. We'll note that the natural log of 1 is 0, so that's going to go away. And this minus sign needs to be distributed inside the brackets to that final term there. We have an ln of 2 and another ln of 2 term, so since those are like terms, we can combine them. We have a negative quantity added to a positive quantity. We can actually flip those around into a more convenient form. Using properties of logarithms, we can take the coefficient and move it up here to become an exponent. We can do that in this case as well. And finally, using another property of logarithms in which subtraction can be rewritten as division, we obtain the following final answer.